Hi, thanks for attending my talk. My name is Dr. Andy May from The Ohio State University. Today I'll be talking about some work we did in a project where we're evaluating low-cost particle sensors, really to understand better how they can be used for indoor air quality monitoring and smart building systems. So I'd like to start by acknowledging our funding source, which was ASHRAE, my collaborator, Dr. Jordan Clark, a PhD student who just has to submit her dissertation for approval, and then she'll be Dr. Yang Zhu, and Mr. Matt Young, who is a former master's student working with Jordan. And I'd also like to thank the project monitoring subcommittee associated with this ASHRAE project, Brent, DJ, Paolo, Li Ping, and Glenn. And then lastly, I'm adding this disclaimer that the use of commercial names does not imply ASHRAE endorsement, approval, or certification. So as we're all likely aware, the marketplace for indoor air quality monitors is rapidly expanding. And so here's just a quick set of snapshots taken from some different brands of low-cost particle sensors that are marketed towards understanding the indoor environment. So some of them have this nice display on the front, so you can see what it's like, in this case, in the living room versus outdoors. Some of these have simpler displays. Some of them have no displays whatsoever. But again, the point is that there's a lot of these, and we don't really know how well they work. And so the overarching question for this project, is how well do they perform in buildings? And so the two questions that I'll be answering in this presentation is, can they reliably detect indoor particle sources, and can they communicate with building automation systems? Some other questions we answered during this project are, what are their upper and lower limits of quantification, or what's the lowest and highest mass concentration that they can reliably report? Then how did the size and composition of the particles affect their performance? And do temperature or relative humidity bias the results? So in terms of the sensors that we tested some bare sensors. So these are the sensors that just come by itself, and we hooked them up to some single board computers to do data acquisition. So we had one from Honeywell, one from Sharp, and one from Plantower. And we tested 5 integrated devices. So 2 of these, the AirThinks IAQ and the TSI Blue Sky, were donated to us as part of this project. And this is back when the Blue Sky was a prototype device. So thanks to AirThinks and TSI for doing that. And then we purchased some of the AirBeam 2s, the Dylos DC 1100 Pros, and some of the Purple Air 2s. And so one thing that I like to spend a little bit of time talking about is that all these sensors are nephelometers. And so what that means is the particles enter into the sensor, they make this turn, they make this other turn. Those turns are separate issues. Here, they're introduced to this light source. They interact with light, scatter the light. It goes through this photoelectric converter, and the signal that's being output is essentially equivalent to what we think about as a scattering coefficient if we're thinking about aerosol interactions with light. These scattering coefficients are essentially the integral of this product of the particle size distribution and the scattering cross-section of each particle size. So we take the product of the size distribution, the scattering cross-section, integrate that over the entire range of diameters, and we get a singular value. And that single value is often related to a mass concentration of particles using some sort of calibration. Of course, the implication of this is that means that these nephelometer type sensors cannot truly distinguish between PM1, PM2.5, and PM10, even though many of them claim to be able to do so. Which, that's another topic for another talk, really. But I did want to highlight that these nephelometers really can't give us any size resolution. And even though they do, it may not be correct. Anyway, onto our results. So this is results from a sort of field study we did on campus. So there's a test home on campus that we basically deployed all of our sensors along with a scanning mobility particle sizer and an aerodynamic particle sizer as reference instruments. We realized that the SNPS and APS aren't sort of truly mass measurements, but this gives us sort of this near real time data set that we can use to compare with the sensors. And so all the data here are 1 minute averages, which is averaging them to the scan time of the SNPS. And so here I've chopped off the figure based on what's shown in our publication here in Science and Technology, the Built Environment. But here we're looking at 4 of the sources that we tested. And so we had multiple repeats of each source, but here's just sort of an example of when we burned incense, when we burned toast, when we opened the window to the test home, and when we sprayed some room deodorizing spray. On the right hand side, the left figure are the time traces of mass concentration, and the right hand side are the average size distribution from the SNPS and APS. And so there's really 2 things that we can note here. The first is that all the sensors are responding to all these sources. So regardless of what the size distributions look like, the sensors are always responding, but the magnitude of the response may be weak in some of these cases. So many of these, we're not really responding to the room deodorizing spray. The second thing that's worth noting is that the magnitude of these responses was quite variable based on the sensor and what the source was. And so that raises the question of how accurate some of these sensors are if we're thinking about something like integrated exposure within the indoor environment. And so these results that we found were similar to previous work done by Brett Singer and Woody Delp at Lawrence Berkeley National Lab, who did some similar tests and got similar results, that the sensors are all generally responding, but the magnitude of those responses sort of varied. And so here's, it's not the same data set, but it's from a laboratory study to kind of highlight the fact that the event exposure is variable based on the sensor and the source. So what I've done here is sort of group together 5 different sources that we tested now in the laboratory, and the bars on the top represent the mean slope of linear regression between the sensors and the reference data, and the bottom panel represents the R-squared value for those linear regressions. And we can see that for ammonium sulfate, just coincidentally, it's right about 1, but we're sort of underestimating the mass concentration for the propane torch soot, underestimating the mass concentration for some Arizona test dust. For the incense particles, it's overestimating the mass concentration, but also it's a lot more variable here. And the same thing with toast. We have a lot of variability, but we're just sort of underestimating the exact mass concentration. So again, the source is something important to consider, but again, that's another story for another day. The second part here that I want to talk about is how well the sensors can communicate with buildings. And the short answer is that they can all communicate with buildings. Of course, this means that they can do it with varying degree of difficulty. So some of the sensors have built-in building communication protocols. So the Aware has BACnet, Zigbee, LAN-Talk, Modbus, MSTP capabilities. The Dylos DC1700, they can produce some custom units that have some of these building communication protocols. And the TSI AeroTrack sensor, if you get a separate room pressure sensor, it can communicate with BACnet. I should mention that these are all based on sort of a market survey that we conducted, I guess roughly about a year ago at this point. Where a lot of these sensors seem to sort of fit is that they can communicate over Wi-Fi and an API. So the sensor can transmit data to the cloud, and the building could pull it back back in using an API. Some of them you need a subscription, so with the Air Quality Egg you need a subscription, with Yoo-Hoo you need a business account. This Air Visual Pro also told us that they have if this then that capability. But at the end of the day, all these sensors output an electrical signal, even the bare sensors. So if you have the software and hardware know-how, you can make it work if you really want to. But one sort of caveat with, I guess especially the cloud-based ones, is that some Wi-Fi networks can pose challenges. So in this Zakova et al. Paper, they identified that strong Wi-Fi signals are necessary to reliably be able to transmit the data, which, depending on where it's located in the building, may or may not have strong Wi-Fi signal. And from our work, there was one sensor that we wanted to test but couldn't, just because it could only transmit data via Wi-Fi connectivity. We didn't have any other options with it. But the security settings on the OSU wireless network did not allow for connection. Some other things quickly. We observed better correlation with longer averaging times. So the right panel is just an inset of the left-hand panel. So here we're going to 6 hours. Here we're going out to 24 hours. And so really, maybe this suggests that we should consider something like 1 hour averaging for continuous ventilation control. I'm not a building scientist, so I'm not the person to give you an answer there. Something else we saw is that increased relative humidity may bias the sensor measurements high. So on the left hand, so two different sources here. The y-axis is the slope of the regression between the sensors and the reference instrument. The x-axis is relative humidity. And in this case, both the reference concentration and the sensor concentration were measured at the elevated RH. And we are seeing that these slopes tend to increase with the higher RH. So that could lead to some problems if we're going to locate these sensors in air intakes depending on the specific climate. And just quickly, that there could be large variability among replicates of a given sensor model. So here's quite large variance among these 66 units, again tested in the Zakova paper, and we saw limited evidence of this with our limited number of sensors. So in summary, these sensors can detect many indoor particle sources, so there's some utility for on-demand air cleaning. I feel like I could strongly claim that. Any sensor can communicate with the building, although there's this varying degree of difficulty. But there are some uncertainties that remain. So obviously the accuracy of the mass concentration the sensor's outputting. If we're interested in sort of an integrated exposure, we may not really have much certainty with that depending on how the sensor's responding. There are many questions, I think, related to reliability and resiliency of the sensors and how that plays a role in decision making. And then of course the time scale of building decision making versus sort of this time scale for a good correlation with the reference instruments that we observed. And so that's it. Thanks for listening. My email's here and some links to the publications that are in peer-reviewed journals.